So this O and this O are called big O notations, right? So this order, we call it order of n and order of n squared. And what does it mean? So to know the to know a certain meaning, we can approach it conceptually or technically, more like practical sense. So conceptually, this big O notation indicates the worst case of the running time. So do you remember that I said, like, what if? What's the worst case scenario of this run time? And the answer to that question is this one, alright? So it's a conceptual approach. If we approach this, if we find out this meaning in more practical sense, this is the right. This is more like in-depth definition. So more like mathematical definition of the big O notations are this. We call a certain function n is equal to order of g n, right? Right? So we call it this. If we go back to the previous example, we have 3n plus 2, right? So we have fn equals 3n plus 2, right? And it was equal to order of gn, and the gn was n, right? And we claim that. And we are going to define these big O notations to have this particular characteristics. We are going to call Fn as big O of Gn, right? Big O of Gn when Fn and Gn satisfies the below. And the conditions are this. So if there are any positive constants c and n0 such that this, right? Then we are going to call it Fn is equal to big O of Gn. So the conditions are, if we write it again, Fn is bigger than Cgn when n is equal or n0, right? M is going to be a positive constant, right? So if we plug in the actual example in the above, we have this 3n plus 2 is always greater. This is Cn is always greater than 3n plus 2 when n is greater than n0. And is there any kind of C or n0 at this moment, right? So that's the question. So what if we said C is going to be 4? So if there are any pair of C and n0, it's going to be true, right? And we are going to set it C equals 4, just 4, and this is an assumption. And then we go back and plug it into the this formula, and I'm going to erase it things a little bit, and we have all these definitions, so I'm going to erase this, right? Okay, and I'm going to go this way, and 3n plus 2 4n, right? And then we can move things a little bit, right? And 2 and n, right? Means that n2 when n0 is equal to, means that n is greater than 2. 3n plus 2 is less than 4n, right? So what if C and n0 pairs become 4 and 2? then there is this pair. There are pairs of the constant C and N0 that satisfies this assumption, right? And we could find out this one example. Because we found this characteristic true, we can call it Fn is equal to order of Gn. Or here n is n, so Fn is equal to order of n. And that's how we find out one function is order of n or order of n squared and so forth, right? So the growth rate of Fn is less than or equal to the growth rate of Gn, right? So Fn grows slowly compared to the Gn, right? So Gn grows much faster and Fn grows a little slower, right? And because of this, Fn is the actual iteration count, right? And this is the worst case of the Fn. Gn is always worse than Fn, right? So we call it as Gn is an upper bound of the Fn, right? So that's that. So if we draw a certain graph with runtime graph with this Fn, this is the one thing that we can find out, right? So the growth rate of Fn is less than or equal to the growth rate of Gn, right? So here the one thing interesting is the term called growth rate, right? And this is one thing that represents the growth rate of various functions, right? And here it says constant. It means the Fn is just a, right? Here I'm going to say just Gn, and Gn is just a constant. And logarithmic function is Gn is equal to log n, right? And linear here is Gn equals n, and n log n is Gn is n log n, and quadratic is Gn is n squared, right? And the cubic is Gn is n cubic, and Gn is exponential n, right? So this graph draws the growth of these functions. As input increases, as input n increases, we can draw the Gns here, and this yellow line represents the En, and this more like reddish line indicates n cubic, and this cyan line is n squared, and this purple line is the n log n, and so forth, right? So this is how things grow when input grows, right? So actually what you can see is that when input grows for a certain period, so for a certain period, here n cubic is bigger than exponential of n. But as input grows, because the growth rate of the exponential is much greater than the cubic function, we can find out after input grows at a certain point, this exponential exceeds than this cubic function, right? So there is a certain point of that, right? So if something grows faster, than the given, that something is the upper bound, that something is the worst case of the given formula, and then this something that grows faster becomes the worst case of the analyzed formula. And that's why we are going to find out the growth rate, right? Okay, so here we are saying that this eventually, in terms of the growth rate, exponential n would be much bigger than n cubic function, and it's going to be bigger than n quadratic, and n log n and n and log n, right? And constant. So this is the order of the growth rate size, and this is really unbeatable. So whenever we say that this algorithm worst case is exponential n, then we are saying correctly. However, in a certain way, it's a correct saying of a kind of really the relaxed estimation. If something grows like the n quadratic, if something grows, if fn is like 3n squared, then the growth rate, this growth rate is asymptotically, here I'm going to retract the word asymptotic because I didn't taught you yet, and we are going to add c here for a constant multiplication here. And if we say this fn is 3n squared, is quadratic function, and its growth rate matches up this case, right? And it's safe to say its worst case is c of exponential n, or c of n cubic. You are not going to wrong about claiming that. However, you are relaxing the worst case scenario estimation, because it's really big growth rate, so it's always going to be the worst case. What you want to have is really the tight estimation of the worst case. Okay, so it's like kind of this concept. So if I claim that its growth rate is c n squared, in other words n squared, then in that case I'm not wrong. And also at the same time I'm saying the exact same growth rate that the fn has. Means that I'm saying the equal growth rate. And that's the asymptotic bounds, asymptotic upper bounds, the tight upper bounds of the of a certain function's growth rate, right? So in that case, see, if fn is given as the squared function, it's alright to say its bigger notation is en, or n cubic, or bigger of the n squared, but the only asymptotically tight estimation of the worst case is going to be order of n squared, right? So I'm going to erase it a little bit. I already explained this, alright, but okay, so exponential function of the c(n) grows more than cubic functions, right? So there is this reverse, this kind of overtake of the exponential function over the cubic function, right? And also quadratic functions grows more than linear function at a certain point, right?